current, or the flow of electrons past a point, has both direction and magnitude. You can think of current as a vector, and current can exist in or through an element. The direction is indicated by arrows, such as a right arrow, a left arrow, an up arrow, or a down arrow. The magnitude is represented by a variable, I1, I2, etc. The units are going to be assumed amps unless otherwise noted. Consider a circuit element that exists between two nodes, A and B, carrying a current I1. Node A is represented by an open circle. Node B is also represented by an open circle. Current I1 is going to flow from node A to node B through our element. Now, I1 has magnitude and direction. Its magnitude is I1, and its direction is from left to right, i.e. node A to node B. We could define I2 going from node B to node A, where I2 would have the same magnitude as I1, but in opposite direction. Based upon the opposing direction of I1 and I2, you could say I1 is equal to minus I2, or I2 is equal to minus I1. Now, voltage, represented by the variable V with units of volts, is a potential that drives a current through or across an element. The voltage across an element, delta V, is the work, represented by lowercase w, required to move a unit positive charge, Q, from the negative terminal to the positive terminal. We can express voltage mathematically as dW dQ. Now note our unit charge in this convention is positive. In reality, an electron is negative. However, when Benjamin Franklin was working with electricity, our unit charge was actually denoted as a positive value. So if we look at the element below, we can describe two potentials. We could have a potential VAB, where we go from a positive terminal A to a negative terminal B. Conversely, we could have VBA, where we go from a positive terminal B to negative terminal A. Now voltage, since it is a potential or a change of voltage between two terminals, also has directionality associated with it. In our subscripts, we go from our positive terminal to our negative terminal. Thus, we have to define a convention based upon our direction of current and the voltage potential across an element. The passive sign convention refers to an element that is a power sink. A passive sign convention refers to an element that is dissipating power within our circuit, such as a resistor. The active sign convention refers to an element that is the power source. This refers to an element that is supplying energy to our system, like a battery. Let us look at these conventions individually. The passive sign convention, abbreviated PSC, means our circuit component is dissipating power within our circuit. Since current has to be conserved, that is, our charge carriers can neither be created nor destroyed, a decrease in power manifests through a decrease in our voltage potential. Therefore, a passive component is decreasing our potential as the current is running through it. The passive sign convention is dictated as follows. If our current is entering terminal A, running through our element, and exiting at terminal B, our voltage potential VAB is going to go from a high potential at terminal A to a low potential at terminal B. Graphically, we could see this as our voltage being a constant value until it reaches terminal A, where it decreases across our element to where it reaches terminal B. The active sign convention, abbreviated ASC, means that our component is providing energy to our circuit. Since our charge carriers have to be conserved, and our current therefore has to be conserved, an increase of power, i.e. when we supply power, means that we have to have an increase of potential. Therefore, an active component is increasing our voltage potential as we go across the element. And this is depicted as follows. Say we have current entering terminal A, going through our element, and exiting at terminal B. Our voltage potential, VAB, is going from a low potential to a high potential. That is, graphically, we enter terminal A with a low potential, and we exit at terminal B with a higher potential. We're increasing the energy within our system. Now let us work with the conventions by looking at four circuits shown to the right. We want to determine if they are a source or a sink. Let's begin by our first circuit. Our current is entering at terminal B, running through our element, and exiting at terminal A. It enters at terminal B at a low potential and exits at terminal A at a higher potential. Thus, we are adding energy to our system in terms of increasing our voltage potential. Element 1 is going to be a source. Now let's look at circuit 2. We have a voltage potential minus VAB between nodes A and B. Now, if we flip this, i.e. we apply the minus sign to this, we would actually have a positive terminal at B and a negative terminal at A. That is, as our current runs through our element from terminal B to A, our voltage potential is going to decrease from a high potential at B to a low potential at A. Thus, element 2 is going to be a sink. Now let's look at element 3. We have a negative current and a voltage potential, VAB. The minus sign in front of our magnitude indicates we can flip the arrow. So our current is actually entering terminal A, going through our element, and exiting at terminal B. We have a voltage potential VAB that goes from a high potential at A and a low potential at B. Thus, as our current runs through the element, our voltage potential is decreasing, and thus we have a sink. Lastly, we have a negative in front of our current magnitude and a negative in front of our voltage potential. These two cancel out. That is, we could say we have a current running from A through our element, exiting B, and we have a low voltage potential at A and a high voltage potential at B. Recall that both our potentials and our currents have directionality associated with them. Thus, our current is entering at a low potential and exiting a high potential. Thus, element 4 is a source.